Welcome to section 8.4. Here we're doing de Moivre's theorem and looking at powers and roots of complex numbers. And so let's consider for a moment a power of a complex number. So let's take the 2 plus 3i. If I asked you to raise that to the second power, no problem. You would do 2 plus 3i times itself. Certainly you wouldn't distribute that 2, then you would fail every subsequent class. But you know that you cannot just distribute powers over sums. You've known that since pre-algebra days when we taught you polynomial multiplication. Same thing. And so we're stuck doing 4 plus 6i plus 6i plus 9i squared. Then going 4 plus 6, well, I'll keep going. 6i minus 9, right? Using that. Then we'll get a minus 5 plus 12i. And that's the square of it. Minus 5 plus 12i. Another complex number. So, what if I asked you to raise it to the third power? What's the process if I ask you to raise it to the third power? And we're staying only in rectangular. So somebody could leave the last section and think, well, polar form's stupid. Jensen's just making us do this. Well, it's not just Jensen, but the math people are making us do this because it's for this reason right here. The only way to do this if this was cubed is to write them both out 3 times. Now, we know what we got out of this one, right? It was 5 plus 12i. Is I think what we got out of that one. Maybe negative 5, right? If I can back up a little bit. Oh, that's too much. Okay, let's just redo it. So if we do this one really quick, and maybe we can take advantage of patterns, we get 4. We know we're going to get a 6i twice, so 12i. And then we're going to get plus 9i squared. And so we do get a negative 5 plus 12i. Now we got a new negative 5 plus 12i plus times 2 plus 3i. So there's no way to avoid that. Now we do the distribution, and we get negative 10 minus 6i plus 24i plus 36i squared. And then we get, and just combine like terms. So imagine how difficult it would be if the 13th power was there, right? There's just no way around doing it one at a time. And so that's where de Moivre comes in. De Moivre figured out a way, using the polar form, to have things really nice. Now, essentially what he did is not earth-shattering. He just paid attention to what was happening in the product one that you and I were able to easily prove with just a simple knowledge of identities. And so de Moivre recognized this, that if you have a complex number, and if n is any natural number, then the following holds. R cosine theta plus I sine theta to the n is equal to r to the n cosine n theta plus I sine n theta. So all you would do is raise r to the nth power and take n times the angle, and you're set. So if we start to look at the examples, they're pretty quick. Like if they're just asking to apply de Moivre's, no problem, right? That happens really fast. So now when you think about taking something to the third power, and it's this guy right here, it's as easy as, well, I got to take the 2 to the third power, cosine I sine of 3 times 120 degrees, right? So what is that? That's 8 cis 360 degrees. Well, think about where 360 degrees is. Don't even think about cosines and sines maybe. It's right there. You're on the real axis and you're out 8. This is the number 8. You could do it that way just by knowing your placement. If you're like, I don't get that, Jensen, well, just answer, what's the cosine of 360 degrees? Well, it's 1. What's the sine of 360 degrees? 0. So now you have 1 plus 0i times 8. So what is that? That's 8, right? So you could go to the cosines and sines, but you could also rely on that case on a picture, right? You can't rely on a picture, I don't think, if you're off the axis. So what about this one? 3 to the third, cis 3 times 40. Well, that's 27 cis 120 degrees. So now what we have to ask ourselves is, what's the cosine of 120 degrees? That's a 60-degree reference angle. It's in the second quadrant, so it's a negative 1/2. Sine would be a positive root 3 over 2. And then you would just distribute the 27. So you see your real and imaginary part. So it could be quick if they keep the angle small. Could be lengthy if we have to go get our polar forms. So think about doing this to the 8th power. That would be terrible rectangle-wise. You'd have to write out 8 of those, right? You could use some pattern types of stuff that would help in there. So I'm not saying there's not shortcuts and all of that, but it's lengthy. It takes far less time for you to say r is equal to the square root of root 2 over 2 squared minus root 2 over 2 squared. Or sorry, plus, and the negatives inside there. So r is equal to the square root of 2/4 or 1/2. And here we're going to get 2/4 or 1/2. So r is equal to the square root of 1, which is 1. Okay, so this is 1 CIS. And I'm going to erase this for a minute. And let's go figure out what our angle is. That's going to be equally as easy. First of all, let's figure out what quadrant we're in, because the quadrant means everything. Right and down. We're down here. Okay, and what tangent? Tangent of theta would be equal to negative root 2 over 2 all over root 2 over 2. It would be sine divided by cosine. And so what's that? Well, that's 1 and negative, I guess, and we know that's 45 degrees reference angle in that 4th quadrant. In that 4th quadrant is 315 degrees. No problem. So we get a nice 315 degrees in there, and we're raising that to the 8th power. Okay, now we got a little bit of work, but again, we'd argue that it's a little bit better, especially when those powers get big like that. And so let me come in here and erase that. So we're definitely in the 4th quadrant. We're over and down. The reason why I'm saying that to myself again is when I sketched out this problem, I had us in the 2nd quadrant, but we're not in the 2nd. We're over and down. We're in that 4th quadrant. So we needed tangent theta to be negative in that 4th quadrant. So we got to figure out what 1 to the 8th is. No problem. CIS 8 times 315 degrees. That's going to be the terrible part, right? Because you know about that. 8 times 315. Whoops. 2520. So ideally we're doing this without the use of a big calculator or something like that could use the trig. It's up to you. I mean, you could take the cosine of 2520. You're going to have that on your exam, and you're going to realize, oh, that's 1. Okay, so the cosine of it is 1. So this is 1 times 1 plus, and if the cosine's 1, you already know what the sine is. Sine should be 0, but let's double check it. Sine is 0. And so we're just dealing with the answer 1. Interesting. That is an 8th root of 1. Okay, so take a look at this something. This number, this 2 root 2 minus 2 root 2i, that complex number to the 8th power was 1. So it's one of the 8th roots of 1 when you're in the complex number system. We're going to be finding some of those. It's going to be interesting, and that's where we're going to next. So we did the powers. Now we're going to move into the roots of the complex numbers. I think I'll just keep this all as one big video. Okay. For any natural number n, the complex number a plus bi is an nth root of the complex number x plus yi if a plus bi to the nth is equal to x plus yi. Let me explain with the last one. Root 2 over 2 minus root 2 over 2i was an 8th root of 1 because root 2 over 2 minus root 2 over 2i to the 8th was equal to 1. A third root of 8, the cubed root of one of the cubed roots of 8 is 2 cosine of 120 plus I sine of 120. It's kind of weird because you're not seeing it in its rectangular form, which is the way we speak, really. So what they'd like us to do is get an idea for this root by using two things. One, your old algebra to come up with the three cube roots of 27, and the other is using de Moivre's theorem to find the three complex roots. And so we'll show you how that's done. It's modeled well in the book as well, so hopefully you're reading the book, but I'm pretty much going to be doing the exact same thing. So let's solve this algebraically. So we're back in intermediate algebra. It's the best way to solve this algebraically is the best way to solve this one. You'll see others where that's not the case. So x cubed minus 27 is equal to 0 is how I would solve it algebraically. I wouldn't take the cubed root of each side. If you take the cubed root of each side, you're going to get only one answer. The cubed root of 27 is 3. It's only going to produce the real number answer. You know there's two other imaginary. In the complex number system, you get all your roots. In the real number system, it only has one cubed root, and that's 3. So this is not the way to go. What is the way to go is what we taught you first. We taught you, before we ever taught you something like the square root property, we taught you to factor. And that's what we would do. So you know how this factors. You learned it back in Algebra 2, I think. I think we held it off and didn't teach it in Algebra 1. It's the cubed root of each, and then you square, change the sign and multiply, and then square. So if you've forgotten how to factor a difference of cubes, go back and review that. It's in your intermediate algebra textbooks. But there's the factorization. So one of the factors is when x minus 3 is equal to 0. And that's the 3 that we already knew. The other two come from solving this. Right? And so this would be a very difficult problem if somebody didn't remember how to factor the difference of two cubes. Right? That's going to be hard. But that's how you'd handle it algebraically. Here we would turn to the quadratic formula and say negative 3 plus or minus the square root of b squared minus 4ac all over 2a. And we're just going through and saying, hey, negative 3 plus or minus the square root. 9 minus 36 is negative 27 all over 2. Okay, that 9 minus 36 is negative 27. Okay, awesome. We're almost done. Negative 3 plus or minus 3 root 3i all over 2. And so what are the two other solutions? Here's one. And the two other ones are negative 3 plus 3 root 3i all over 2. And the other is negative 3 minus 3 root 3i all over 2. So the three box numbers are the three cubed roots of 27. Solving that equation. There's three numbers that you can plug in there that will all equal that. Okay, solving using de Moivre's theorem. Okay, and so I'll do some writing here to help you follow along. And they got a big blank space down here, so I think we'll be okay. Okay, so here's what we do. And it's very interesting. They'll model the same thing in the back. To find the three complex roots of 27, we look at a complex number and assume it is a root. Okay, so we build it, for lack of a better way to say that. So we need our cosines of some angle, which they typically call alpha when we're looking for it, plus I sine of alpha. We need that raised to the third power to be something. We need it to be 27 times cosine of 0 degrees plus I sine of 0 degrees. So this is the polar form of 27. So if we're going to use de Moivre's, we need to get the polar form of 27. Where is 27? Right on the x-axis. So what angle are we up? We're up none, right? So that's its polar form. Grabbing it like that. And let me get an eraser in here. So what do? Well, let's use de Moivre's theorem. And so this is going to essentially prove something that's going to come up on the next page, which is the complex root theorem. So you know de Moivre's theorem. De Moivre's theorem says this is r to the third cosine 3 alpha plus I sine 3 alpha, then would need to be equal to 27 cosine 0 degrees plus I sine 0 degrees. So what do we know? Well, we know r cubed has to hook up with 27, and we know cosine 3 alpha needs to be equal to cosine of 0 degrees. And sine of 3 alpha needs to be equal to the sine of 0 degrees. So what does that mean? It means that 3 alpha needs to be equal to 0 degrees or some coterminal angle with that. Okay, you only need one of those, right? But we have this link between 3 alpha and 0. Let me erase that. That didn't come out as nice as I'd wanted it. Let me use a highlighter. We have this link between 3 alpha and 0. But you and I know from our work with solving equations that you would, if you have a 3 alpha in there, there's going to be multiple times between 0 and 360. In fact, we know 3 times that that's going to happen. So what we do is we solve for the alphas that will work. So again, we set r cubed equal to 27, and the trig equations equal to one another. So it tells us that those angles have to be equal or coterminal with 0. That's where the 360 comes in, because it could be coterminal. Now we're going to divide everything by 3. 0 degrees divided by 3 is still 0 degrees. 360 divided by 3 is 120 degrees. So these are all of our alphas. Our alphas are all 120k for k equals 0, k equals 1, and k equals 2. Always one number less than the power that you're looking at. Notice we'll get 3 different angles there. So I'm running out of room here, but we're going to go build our answers. Okay, so remember what r is. R cubed is 27, so r is equal to 3. So one of our answers is 3 CIS 0 degrees, right? So the 3 degrees are alpha 1, 0 degrees. Alpha 2, 0 degrees plus 120, which is 120 degrees. And alpha 3 is 0 degrees plus 120 times 2, or 240 degrees. 0 degrees, 120 degrees, 240 degrees. Well, 3 CIS, so one of our answers is 3 CIS 0. The other is 3 CIS 120. And the other is 3 CIS 240. Again, let me just back up. So this is coming from setting the angles equal to one another. We pick k's always starting at 0, and you know there's 3 cubed roots of a number, so we're going to stop at the third number. So it's always one less than the power that you're dealing with is where you stop your k. These are our 3 answers. Now they don't want them like this. They want them in a recognizable form to you, which is the rectangular form. So because I'm out of space, I'm going to build my answers up. You could come back to these, but we need to compare these. There's a reason why they're asking us to do it doing de Moivre's and others. So if we take a look at what we did with de Moivre's, we just assumed we had a root and then built what it had to look like and came up with this. So really good mathematics there. Very representative of where you're going with all of this. More thinking than robotics is what we need out of this whole experience. So let's take them one at a time. 3 CIS 0. That's 3 times cosine of 0, which is 1, plus I sine of 0, which is sine of 0 is 0. So we get 3 out of this. What 3? This same 3 that's right here. Right? What else are we going to get? Well, we're going to get 3 CIS 120. So 3 CIS 120 degrees is 3 times the cosine of 120 degrees Well, 120 degrees has a 60-degree reference angle, so that's negative 1/2 because it's in the second quadrant. But it's going to be plus because it's in the second quadrant, root 3 over 2I. And so what do we get out of this? Negative 3 over 2 plus 3 root 3 over 2I. Let me put that together as a single fraction and see if you recognize it. It's right there. It's the plus part of that answer. And so we get our second one. And guess what we get when we get 3 CIS 240? And what do we get out of that? Well, we get 3. And 240 is also a 60-degree reference angle, but in the third quadrant. So we get negative 1/2 minus root 3 over 2I. And we get the negative 3 over 2 minus 3 root 3 over 2I. And we get the exact same solutions that we got out of the quadratic formula. So somebody looking at this is going to say, oh, we should just use the quadratic formula. Keep in mind that it's going to be a lengthy process if you're looking for fourth roots, 8 roots. In one step, we were able to get down to a quadratic here. That's what made it fast. And if you don't remember how to factor a cube, it's going to be impossible, right, in order for you to come up with that algebraically. Okay, what we need to recognize is the power of what's happening here. And so what's happening on this next page is they're condensing down what we observed in that process. If you want to find the nth root of a number, you're going to take the nth root of that number and you're going to have some alphas, and you can have as many alphas as you have roots, and those alphas will all be generated in this same way. So you can bring this notes to you, but this is the condensed version of what we just observed. So as we go through the next 3 problems, we're going to be using this nth root theorem. So now they want us to find all the cubed roots of negative 27, leave answers in polar and rectangular forms. Okay, so what are we going to do? First thing we're going to do is recognize what negative 27 is in its polar form. It is 27 CIS 180 degrees. Do you see that? Negative 27 would be out here, right? 27 marks away, and it would be this line right here. That's 180 degrees. That's the best way to find it. The other way to find it would be to do the angle measurements and things that are there on this. But when you're on an axis, you can just name it just like that. So it's going to have how many roots? It's going to have 3 roots. So we're going to get those by letting k equal 0, k equal 1, and k equals 2. So what are the roots? Well, it's telling us that the roots are like this. The cubed root of negative 27 CIS alpha. Okay, where alpha is equal to 180 degrees divide plus 360 degrees, each divided by 3, and we have a k on there. So I'm just following that formula. We're going to get alpha over n plus 360 degrees over 3k, or either over n, right? Alpha over n minus or plus 360 over n, and our n in this case is 3. And so what is our k going to be? K equals 0, 1, and 2. So R1 is going to be, well, what is the cubed root of negative 27? It's oh, I'm sorry, it's not of negative 27, it's of r. That's where I was going wrong. So it's the cubed root of r, which is 27. So that's 3 CIS. And the first angle would be letting k equal 0. Well, if you let k equal 0, you got 180 degrees divided by 3. That's 60 degrees. R2 is going to be 3 CIS. And maybe it would help if I put these out. So alpha 1 is going to be 180 degrees over 3 plus 360 degrees over 3 times 0. That's where I came up with that 60. So what's alpha 2? It's 180. It's the 60, right? So this is 60 plus 120 times 1. It's always 1 less. So here we're going to get 180 degrees. And R3 is going to be 3 CIS, and we're going to then add 2 of these guys. So that's 240 plus 60, that's 300 degrees. So 60 degrees, 180 degrees, and 300 degrees. You'll start to see some patterns in there that you can utilize, but they want us to go through this process, right? Letting k equal 0 for the first one, 1 for the second, 2 for the third. So I'm erasing this so that we can write our answers, because I think you know what the cosine of 60 degrees is. It's 1/2 sine root 3 over 2i. And what do we get? 3/2 plus 3 root 3 over 2i. So there it is in its polar and its rectangular form. And you can put that all as a solid fraction. You know what this one's going to be. 3 times cosine of 180 is -1. Sine of 180 is 0. And of course we're going to get a -3, which is the cube root that's in the real number system that we all would have said in our arithmetic classes. And then what's going to happen here? 300 degrees, that's a 60-degree reference angle in the fourth quadrant. So my sine is, my cosine is positive and my sine is negative. And notice they come in conjugate pairs like they should. Awesome. And that's how we get the cube root. Now, I don't know why they want this. I would not put this on the exam, but they want us to graph each cube root as a vector in the complex plane. Well, don't look at its algebraic representation. It's very easy to do this. It's not a hard problem to graph each one. Look at its polar form. So let me underline in red the first one. 60 degrees. Let's say it's this, and we're going out 1, 2, 3. Here's your first one. There's a 60-degree one. Let's go blue. 180, 1, 2, 3 out. Here's your other one. Second one, I shouldn't say the other. There's the second one. 300 degrees, 60-degree reference angle. Let me go green on this one. 60-degree reference angle from the bar there. 1, 2, 3. It's this guy right here, right? Maybe they want you to see how easy it is to get those representations there, or just to see those things cubed would be equal to -27 coming out pretty easily. So, how are we going to finish out? More roots. Find and graph all the fourth roots of I. Perfect. So let's talk about what I equals. Where is I? Here it is. What's that magnitude? That's a magnitude of 1, and that's at a 90-degree angle. So that's what I is equal to. If we want to find the fourth roots of I, well, the fourth roots of I, I'll call the roots themselves, are going to be the fourth root of 1, CIS, times some angles, right? Now, what are those angles? Those angles are 90 degrees divided by 4 plus 360 degrees divided by 4k, where k starts at 0, then goes to 1, then goes to 2, then goes to 3, always 1 less. And that makes sense that we would get 4 roots out of that. So let's go find out all of our angles. The first angle is going to be 90 degrees divided by 4, right? And so we're going to do 90 degrees divided by 4. So it says find and graph all those roots. And here, if 90 divided by 4 is going to be 45 divided by 2, so 22.5 degrees. And maybe that's what you do, 22.5, sorry, had two things in my mind at the same time. This is really 22.5 degrees plus 360 divided by 4 is 90 degrees k, right? Maybe that's a better switch out. So when k equals 0, for alpha 1, we get 22.5. What about when k equals 2? Well, there I'm going to take 100. I'm going to take 1 sorry, when k equals 1 for alpha 2, I'm going to take 90 and add 225. So essentially you're just adding 90 however many times, 4 times. And so we're going to get 112.5 degrees. Alpha 3 is going to be 90 more than that. That's all that's happening every time. So just to truncate it down a little bit, we're just keeping adding 90 however many times, 202.5 degrees. And then adding 90 to that would be 292.5 degrees. Those are your 4 angles. Now, it doesn't say that we have to put them in the rectangular form. So if it doesn't tell us to put it in the rectangular form, we're going to not put it in rectangular form, especially when they're angles that we don't know. So what's the first root out of many? Well, the fourth root of 1 is 1, CIS, 22.5 degrees. R2 is going to be 1 CIS of 112.5 degrees. R3 is going to be 1 CIS of 202.5 degrees. And R4 is going to be 1 CIS of 292.5 degrees. I think you can leave it like that. I haven't verified, but if you look in the back of the book and it has it in rectangular form, go ahead and put it in rectangular form by running it through your calculator. We'll not know those numbers, and you'll have to put the decimals in there since we don't know what they are in their exact form, right? And so here are your 4 roots to I. All the 4th roots of I. Each one of those numbers to the 4th power would be equal to I. Pretty interesting as we go through, but you would see that especially if we use de Moivre's theorem. Like, it would not be hard, because let me just grab R1 for lack of a better reason. R1 to the 4th would be 1 CIS of 22.5 degrees to the 4th, which would be 1 CIS, and 22.5 times 4? 22.5 times 4 is 90, I think. Let's check that out. Or maybe I'm not thinking about that right. And it wouldn't be 22.5 to the 4th. It would be times 4. Sorry about that. Yeah, it's 90. Yeah, doubled is 45. Doubled that is 90. And so what is 1 CAS 90? Well, that's 1. Cosine of 90 is 0. Sine of 90 is 1. I. And look what we get. We get I. Each one of those is going to work out that way and going to give us I when we take it to the 4th power if we wanted to check ourselves out. So my point in showing that is that they work. It does ask you to graph it. Again, I won't do that on the exam, but that's pretty easy. Don't stress about that. Just go put them in their right forms and go one out from a 22.5 degree angle. Solve all complex solutions, leave answer in rectangular form. So the reason why they're doing cubes is to keep your work small, but we would be wanting to find out x cubed equals -1. We would be wanting to find out all the cube roots of -1, and they're suggesting that we rewrite -1 in its complex form, which would be CIS 180. So that's what that is. Remember what you have. You have -1 plus 0i, right? That's what that guy is. And so as you go to find its magnitude is going to be 1. As you go to find its angle, you'll find out that that angle is at 180 degrees, and very quickly coming off of that. And so that's what we have. So what do we know? We know that our roots is going to be the cubed root of 1, which is 1 CIS of some angle. R2 is going to be 1 CIS of some angle. And R3 is going to be 1 CIS of some angle. Now, what angle will that be? It's going to be 180 degrees divided by 3 plus 360 divided by 3k. Letting k be equal to 0, 1, and 2. So we want to get as much out of going back and looking at the formula as possible. So 180 degrees divided by 3 is 60 degrees plus 120 degrees K. And first of all, we're going to let K be nothing, and so we're going to get 60 degrees. What this is saying is start with 60 and add 120, however many times you need it. Well, we know there's only 3 roots, so adding 120 is 180. Adding 120 is 300, right? Coming up with those different ones. And so they do want it in its rectangular form. This is how they want the answer. And so cosine of 60 degrees, 1/2. So we're getting 1/2 plus I sine, or no, plus I times root 3 over 2. Sorry, I was going to write the 60, but I don't know why. And so what's this one going to be? 180 degrees, so it's completely real. But in the negative direction, so that's going to be -1. 300 degrees is 60-degree reference angle in the 4th quadrant, so cosine still positive, but sine is negative. And so let me fix this one up here. It's bothering me. So remember, this was 1, and both the cosine and sine were positive. Root 3 over 2 has the I. So all 3 of those are the cubed roots of that. And so you'll see those in your homework problems. They're done very, very similarly to this. But that's it for the 8.4 direction. And you can see the problems are going to take you a little bit of time. But you should expect to have some on the exam, because it really is the culmination of why, at least from our perspective right now in just a trigonometry class, why we would introduce a polar form.